behind sprinklers. There's a Adobe update on the computer. Well, basically, when we were walking in the park, I ran across this sprinkler and reminded me of a question I had in my thermodynamics class. That was, why can water just flow out of the sprinkler but can never go back? If we just take a movie, laws of classical mechanics are supposed to be time reversible, but if we film a sprinkler and watch it in reverse, there's something wrong with having water flowing back into the sprinkler. So these kind of thought experiments are kind of funny in a peculiar way. So I want to go a bit further in there. So indeed, how can time-reversible laws of motions give rise to reversible processes? Well, to understand that, I'll give you first a few examples of irreversible processes in nature. Well, sprinklers, like I just explained, there's also waterfalls. So if you film a waterfall and watch it in reverse, there's something wrong about having water just flow up. The Doppler effect is a different kind of irreversible process because it has to do with the velocities. Because if you just watch a train and there's nothing wrong with the movement, I mean, if it goes from left to right or right to left, you won't be able to say which one is reverse, which one is forward. But if you add the sound, what happens is that the good one will have a high frequency and low after, but the opposite will not be true. So there's something wrong about having a train going from low to high frequency. But this has to do if we take t to be minus t, the velocities change, whereas acceleration and position will not change. But still, it's kind of something wrong if we film it backwards. If we look at a man crossing and non-crossing is like, if we just take a movie of that, there's nothing wrong on the surface. But if you look deeper in the picture, what happens is that you will notice that the man in the reverse video is blind because photons exit his eyes. This one will be inhaling carbon dioxide. He will be exhaling oxygen. So there's something wrong if you look closer. So why is that? So to understand a bit deeper those processes, we need to know what entropy is. So it's going to be a reminder of your thermodynamics class. Then that will lead us to Loschmidt's paradox, which is a counterargument to Boltzmann H theorem, which is solved by the fluctuation theorem. So entropy, as you all know, is kind of an obscure concept. I never got a hang of it really, so that's why I decided to do this. We can define mathematically a small change in entropy as a small change in heat divided by temperature. But that doesn't give us a good insight of what entropy really is. So physically, if we go on the macroscopic level, we can view entropy as the availability of a system to do work. So if you remind your engines class where waste heat is closely related to the entropy, well, you see that, and also to the free energies, entropy is a measure of the availability or inavailability of the system's energy to do work. We can also view entropy as as nature's way of just spreading energy, because energy doesn't want to be localized, it wants to be spread out. So it's just a macroscopical way of saying that when energy is spread out, the accessible states of the systems, there are more accessible states, so entropy is higher, which will lead us to the microscopic case on the next slide. So the 19th century has led physicists to establish the second law of thermodynamics, which states that the global increase in entropy, the global entropy in the universe must always increase. So there can be local loss, but globally it has always to be positive. So entropy has been the first and is one of the only, except for a few quantum field effects, is the first quantity that requires a direction for time. So entropy distinguishes between past and future. So it's kind of odd. And some people relate the arrow of entropy to the arrow of time. So if we look at the microscopical level though, what happens is that we can view entropy as a measure of the disorder inside of a system because it's linked to the number of available states with Boltzmann's formula. So this makes the second law of thermodynamics a mechanical statistical one, because to know that, we have to know the different available states. We need to have information about the positions and the velocities of our molecules. So in that view, we can view an equilibrium state as perfect internal disorder, because if we just take an example of a drop of dye in water, at first it's all localized, and then as time goes on, the dye just goes everywhere in the water, and at the end, when it reaches equilibrium, we have lost all information about the initial conditions. So entropy can also be viewed as ignorance. So yeah, just to see how weird that is, or how confusing that view of entropy is, if we assume that all microstates have equal probability of happening, let's just calculate the probability of one having all the particles in one half of the box. It goes as 1/2 to the power n, which goes to 0 as n is large. So for a mole of gas, what happens is that there is at least 2 to the 10 to the 23 available states. That's kind of hard to calculate. So what happens is that the question we still get a hint of why things shouldn't go backwards because of entropy, but I'd like to have a quantitative value of calculating probabilities. But still the paradox remains, how can irreversible processes can be deduced from time-symmetric dynamics? It shouldn't be like that, yet it happens. So Boltzmann has proved this H theorem, which states that for an ideal gas, S can only increase as a function of time. Thing is, this is a proof of statistical mechanics, so it's supposed to be on the laws of motion, which are time-reversible. But yet, he made an assumption that is flawed, and that's what Lockschmidt has replied to him. He assumed molecular chaos, which means that the momentums of the molecules should be uncorrelated and independent, but it's not true, because if you look at the picture, if you look at the collision between the molecules, well, the velocities after that will certainly be related. But this assumption is needed to prove the H theorem. So there's something flawed because it changes the conceptual system of statistical mechanics. We want to look at the microscopic level. We want to have the equations of motions to be the same. So it introduces a time asymmetry because we should be able to go from time 1 to time 2, but also in the reverse order, and assuming that the molecular chaos assumption doesn't do that. So the question remains, is there a way to formally deduce irreversible processes from time-reversible dynamics without assuming any bad hypothesis? So the answer is yes, we can. And how can we do that? It's the fluctuation theorem, of which I will give you, like the Crookes fluctuation theorem is part of the greater fluctuation theorem. But yeah, basically, since the second law is a statistical one, there should be a non-zero probability of having decreasing entropy. So can we quantify this probability? It turns out that we can. So if we take A and B to be two microstates that are not at equilibrium, then Crookes fluctuation theorem states that if we look at their difference in the Helmholtz free energy and at the work that the system does while going from state A to B, then the ratio of the probability of going from A to B to the probability of going from B to A, so the inverse processes, are given by a factor of the exponential of the work minus the free energy. So that is great because this proof is obtained purely by statistical mechanics, which assumes that the equations of motions are time reversible. Yet we obtain that entropy can decrease. It's just very unlikely because the exponential will be very, very, very low. So in conclusion, if we look at the macroscopical level, we can say that with entropy, well, energy for a waterfall to fall, energy has been spread out in sound waves and heat loss. So all this energy could not just combine to just take the water up the fall. If we look at the microscopical level for the fluctuation theorem, well, for the sprinkler, the work to be done by the pressure to take the water from the outside into the sprinkler makes the probability of having the reverse process ridiculously low. And the second law of thermodynamics, well, can be broken because it's statistical, but it's very unlikely. And what I would like you to remember is that irreversible processes can be deduced from time-reversible mechanisms. Thank you.